So we've talked about variables and we've talked about conditional expressions. Now let's talk about functions. So we're going to talk about what functions are, how do we make them, how do we write them, how do we use them. Uh, we can pass values to them and we can get values out. That's kind of the whole point of a function, is changing something or getting a new value. So if you can think back to algebra or geometry, we've got the linear equation, y equals mx plus b. So here we've got a linear equation or a function named linear equation, and we pass it three values, m, x, and b. And if you remember the linear equation from geometry or algebra, it's m times x plus b. So m is the slope, x is what we call the independent variable, and b is called the y-intercept. So if you were to do a value of 0 for x, it doesn't matter what the slope is. B tells you where this function or where this line touches the y-axis at the value of 0. And then the slope gives you the slope of the line. So rise over run, if you remember that. So this is what a function looks like in C. We tell it, okay, first of all, I want a float value to come back. So remember that a float value is a number that may have a fractional component, so a decimal point. And so this is saying, give me a float value back. Then we have the name of the function, and then we have what are called arguments. And we have to say, this is the type for the argument that you can expect, and here's the name of the argument. Now, what we name the arguments in the function doesn't have to match when we call the function. This is just kind of declaring, this is what I, as the function, am going to refer to these variables as. So, to use the function, here's kind of what it looks like. In our main, we can say, declare a loop and say for float x equals -4. So remember, this is going to start at -4. Then I've got our conditional equation or our conditional expression. So while x is less than or equal to 5, do this stuff. And then we're going to increment by 0.1. And you could do something else, but in this case, we're just doing an example of 0.1. So then within the function, we do float y equals linear equation, and then we do our slope, and in this case, we're going to do 0.5. We're going to do an x, and that's just whatever value we have in our loop, and then -1. And so if we look at our graph, then we call graph xy. So this is just some function that draws a graph. We're not going to worry about that too much in this talk. This is just kind of an assumed thing to exist. Then we declare that function right here the same way we just talked about it in the last slide. So you can see if we do x of 0, we should intercept y at -1. So here's the y-axis, and indeed it does touch at -1. And then we have a slope of 0.5, which means that it's going to go up 1 every time it goes to the right 2. And if we go to the left, it's going to go down 1 and over 2. And again, we see exactly that. This goes up 1 and over 2. It goes down 1 and over 2. And this goes from -4 to 5, which is exactly what we said right here. So what this is going to do, it's going to iterate from -4 and then -3.9 and then -3.8. And then it's going to pass those values to the linear equation right here, which is declared down here. This is going to take those values in, 0.5, x, and -1. And it's going to return 0.5 times x plus -1 back to y. And so that function is going to execute. It's going to return a value, which is right here, and it's going to stick that into y, and then we're going to graph the x and the y values. So that's kind of how functions work. So if we were to map that again into memory, like what does the compiler do with all this stuff? Well, it's going to get each of these values, mx and b, and that's going to be separate instructions, but I've just kind of laid it all out in one right here just for convenience. Then in the next instruction, we say for this thing, so we go to 1100 down here, or I'm sorry, this is our function call. So 1100 is where the compiler sticks the function in. So it's going to say y times mx plus b, store y somewhere where it's going to be accessible to main. And then it's going to go back to 1008. So it's going to get y from wherever it was stored. Then we've got this graph function, so go to 1200 down here. So that graph function is going to get x and y values. Then it's going to draw x and y, whatever that graphing function looks like. That's going to be a bunch of instructions. And then once that's done, it's going to go back to 1016, which is up here, and that's our loop. So if x is less than or equal to 5, go to 1004. So it goes back up here. And I guess I left out the iteration part, but you can kind of see how this maps into memory. So the point here is that we've got our main instructions, they're all right here. And then the linear equation instructions, they're stuck in a different part of memory. And so we're going to jump down to that part, do the stuff that's associated with that function, then come back to main and do the stuff in here. Then it's going to jump to this graph instruction set, or this graph function, which is yet another different part of memory. That's going to execute, then it's going to come back to main, and then it's going to do the loop as part of the main. So the point here is that each function gets its own separate memory address in memory, and it's called linking and loading at runtime, where it's going to like store these different functions in different parts of memory, and they don't necessarily have to be contiguous. They can be kind of wherever it fits. So, so what we've seen so far, what does a function need to have? Well, it's got to have a name. We can pass it arguments, although we don't have to. In the case of the linear equation, we have to, but we could hard code a linear equation of m and b, for example, and then only pass it x. Or we could just have a single function that just is hard coding mx and b, and that all it does is returns the values for that. We've also got a return type, which is also optional. So in this case, we're using a return type of float, but we could have a function that does not return a value at all, and it only operates on this stuff. And in that case, maybe we want to change the state in a different way, or if it's not this sort of equation, or we might pass the value that we want into the equation and have it change the value through passing it as an argument. And we're going to talk about that in a little bit later. Now, what can a function do? Well, it can do operations, and if you passed it arguments, it'll use those arguments. It can change state information. This is something you want to be careful about, but it can do that. And then it can return a value. And again, that's optional. It kind of depends on what you want to do. So basically, a function is a way of taking code out of your main function and putting it somewhere else. And you might want to do that because you're going to be doing that over and over and over. Just like in this graphing equation, it makes sense to put this out here because maybe this isn't the only time we're ever going to use the linear equation. And indeed, probably not. We could see using this linear equation in many different contexts, not just in this one program. So we can make this separate, and then other programs can call it. Okay, so in a C-style function, again, how do we write one? Well, we put the return type here first, and this tells the compiler, this is what I expect to get back. Then we give it the function name, and then we can give it 0 or more arguments. And so this notation with brackets and a star, this star means 0 or more of what is in the brackets. And then again, we give the type of the argument and then the argument name. We've got operations, so just whatever the function does. And then this is an optional thing. I would give it a return type, or return, the keyword return, and then data of return type, whatever this type is. So again, in our linear equation, this was return, and it was a float value. And so that's what we've got right here is return type, and we want to return data of this type, whatever is specified. If you're not going to return anything in a C-style function, you would say void, and void just says I'm not going to return anything. Okay, so again, mapping that to our linear equation, we've got return type, that was float, function name is linear equation, and then in this case there was the first argument was of type float, m is the name, second argument was float x, and then float b, and then we've got operations in there. So again, here's the equation, float linear equation, float m, float x, float b, and then we do return m times x plus b. Okay, so arguments. This is stuff inside the parentheses. So if we've got this int foo, type 0, argument 0, type 1, argument 1, type 2, argument 2, on and on and on. The stuff in here, in the parentheses, those are called arguments. And that's just data that we want to pass to the function. So again, float linear equation, float slope, float x, float y-intercept. Now there's two ways we can pass data to the function. There's pass by value and there's pass by reference. So pass by value is, okay, I've got my x value here that I've created from our loop that we had before. Here's the value that I want you to use. Now, so what that's going to do is take a copy of the value of x and pass it to the function. Now, some languages won't let you change that value. Other languages like C, you can change the value, but since all you have is a copy of the value, if you change it, me being the one who passed it to you, I'll never know. I just gave you a copy. So if you mess with it, if you delete it, if you change it in any way, I'll never know because I kept my value. I just gave you a copy. Pass by reference is different. Pass by reference is, okay, I'm going to give you a reference to my value, but if you change it, that means you're actually changing the value of the thing that I told you where it lives in memory. So this is the actual data. This is the address of the data. It's where this data lives. If you change the data, then you're not only changing it for yourself, you're also changing it for me. And so this is why this can lead to many different errors if you don't know what's actually going on in your language. So it can be unsafe if you're not ready for that. And in the functional programming world, this is called side effects. So side effects is, well, you're doing the function that I want you to do, but you're also having the side effect of changing this value. Now you can do that intentionally. You can say, well, I want to do it exactly that way. I'm setting up this function to do it that way. And so that's just what I want to do. You can absolutely do that. You just have to be aware of the fact that that is how you're doing it. And in some languages, you're actually not able to do that. So like functional languages, for example, they're designed to, instead of changing the value of the thing that you pass, they're just designed to return a value of the type that you want. Okay, so again, that's side effects. You execute a function and the function changes state without your express knowledge. So you want to avoid that. Again, you can do it as long as you are very aware of the fact that that is why you're doing this. So why do we use functions? Why not just put everything in line? Well, it makes our code reusable, and it also makes it easy to maintain. So you can reuse it again because you could create a library of functions, which is exactly what many languages do. They'll have a standard library, and that will just be functions that were written by the people who wrote the compiler or wrote stuff for that language that they know is going to be used very frequently. So typically this will be stuff like printing to the console, or math equations that are used all the time. So like sine, cosine, tangent, all that stuff. Maybe the value of pi. And many other things that are just commonly used over and over and over. Languages will often provide a library of those functions, and then you don't have to use them yourself. You can reuse the functions that someone else has written and tested and, battle tested, basically. It's also for ease of maintenance. So let's say we were to use that linear equation, and, it's a pretty simple function. Why not just write that function every time we need to use it? Well, if there was a little bug, maybe I, did mx minus b or something, and then I just copy and pasted that code 300 different times. Well, now I'm going to have to go and find every instance of where I copied it once I figure out that that's a bug. I'm going to have to go and look at every single time I copied it and change it every single time. And if I miss one, well, that bug still exists. So by having all of that functionality of this exact thing that I want in one spot, all I have to do is maintain it in that one spot. And so that makes maintenance easy. So if I realize there's a bug, I just fix it once, and then I never have to fix it again because I've fixed it where that code lives. Okay, so returning. Again, you can kind of think of, not only is this function giving a value back, you can almost think of it as this is the value of this function given these arguments. So when I say this thing is going to return a float value, it absolutely has to return a float value. In many languages, your compiler will give an error if you don't return a float value ever, or in every code path. So the compiler sort of helps you out sometimes, and it says, hey, you said you were going to return a float value and you didn't. You should probably do that. And again, if you don't want to return a type, then often you'll just say void, and that just tells the compiler, hey, I'm not returning anything. That's intentional. So don't worry about that. Think back to the first discussion on variables. We talked about this model of the computer. And so we have memory, and in memory, we have instructions for the operating system. We have application instructions, and then we have an application space. And the way you can kind of think of this is that each function is allocated what's called a frame in what's called the stack. So you can think about a stack as like a stack of books. So the way a stack works is it's last in, first out, LIFO. So that means your main will be on the very bottom of the stack, and any variables you declare for main, this is where they're going to be stored in memory. Then when you execute a function, all of that stuff is stored on the stack, and then a new frame is created on top. Then once that function ends, that frame is stripped away, and it goes back to the bottom of the stack, or the next thing underneath. So last in, first out, if you think about it, if you go 0, 1, 2, 3, then you want to get all that stuff back. Well, if you pop from the stack, meaning remove the current value, it's going to be the last value that was in. So 0, 1, 2, 3, when you say, give me the one that I gave you last, that's 3. Then if you do, okay, now I'm back to 2, so give me 2. Then give me the next one, it's 1. Give me the next one, it's 0. And then the stack is empty. So if you were to do 0, 1, 2, 3, give me the current one back to 2. Okay, now I'm going to give you another value, 4. Then 4 is on top. Then you say, give me what's on top, 4, 2, 1, 0. In programming, when a function is invoked, all the local variables that you've created, they're stored to the stack. Then you create space for a return value of the function so you can get it back. Then you create a new stack entry for the function, store the address of the next instruction of your current function, or your current function to the stack, and then you go to the new function. So that's a lot of stuff, but just keep in mind that all your variables are stored in that memory space, and you have like a pointer to your next instruction in that function. So that's when a function is invoked. You store the variables, you create a space for the return of the function, you create a new stack entry for the new function, and you store the address of the next instruction of their current function. Then you go to the new function. Then that function executes, then it returns. So what you do is you store its return value in this space. You delete that whole frame, its entry, from the stack, and then you go to the next instruction of the lower stack entry. So it just moves right along. Maybe we have two functions. We've got a quadratic equation and a square. So square just returns x times x. Our quadratic equation is y equals y times a plus b times x plus c. And what is y? Well, y is the square of x. So this is x squared times a plus b times x plus c. So that's a quadratic equation. So here we've got main float y equals the quadratic equation of these variables a, x, b, and c. So we've got our quadratic equation that takes all of those variables in. We do y equals square of x, so x squared. So y equals y times a plus b times x plus c, and then we return y. And then square is just x times x, so it's the square, x squared. So in our stack, what this is going to look like, we've got main, and it's got, the local variables, a, x, b, and c in this case, if we had declared them up here, and as well as y. So once main calls quad, then we create a stack frame for the quadratic function, and it's going to store a, x, b, c, and y, as well as the next instruction of main, where we're going to go to once this function is done. Then, so the quadratic equation calls square, so we create yet another stack frame for square, and that's going to store x and the next instruction of the quadratic equation. So this one, square is going to calculate its stuff. It's going to do x times x and return x squared, which is y. So that gets stuck into y. This whole frame is then deleted, and we come back into the next instruction of quad, which is right here. Then it calculates this stuff. Then it returns y. So y is written into main. This frame for quad is deleted from memory. And then main goes on and it does its stuff. So it would maybe graph that or something. We didn't write it in there. But so then all that's left on the stack is just the main. And then once main is done, then this stack entry can be deleted. And then we're all set. Okay, so once again, argument passing, we can pass by value or we can pass by reference. So when we pass a variable's value, the value of the argument is written into that new stack entry, the new frame. But when we pass by reference, we write the address of the argument. Now, typically what this is going to be, if you created a local variable, it's going to give it the address of the local variable right here in the stack frame. If you allocated it outside of the stack, because maybe it's a dynamic data structure, it's going to give it the address over there. It doesn't really matter. If this is called the stack, the other memory where you do like dynamic allocation, that's called the heap. And we'll talk more about that later. But for now, just know it doesn't matter where the variable is. To the computer, it's all just addresses in memory. As long as it's within this application space, this is where your computer or your operating system is going to allocate the variables. So whether it's in the stack or whether it's in the heap, like outside of the stack, it doesn't matter. It's all just addresses. So you can give it the address of the argument. So let's look at some actual code in VS Code and kind of map all of what we've talked about so far to a real example of code that is actually going to run. So in VS Code and in many other editors and developers, you can actually see the values of your variables, and you can tell the program, or you can tell VS Code, hey, stop at this particular line and show me what's going on all over my program. Show me the values of the variables, show me what the call stack looks like, show me all of that. So in order to set what's called a breakpoint, where you say, oh, I want to see the values of stuff, you just go right over here and just toggle this little red dot. And that's going to say, when I run the program, I want you to stop there and show me exactly what's going on. So that's a pretty nice feature in IDEs and VS Code and other editors and debuggers. So up here, rather than saying just run, which would just run without all that stuff, we're going to say debug. Okay, so this is going to go right through, set everything up, and it's going to stop at the very first breakpoint, which is in our main function down here. So we say float equals linear equation 0.5 x negative 1. And so we can see what are the values of these variables. Well, so y is negative, or is just some uninitialized value, because we just say float y equals that, but we've initialized x to negative 1 in this for loop. Okay, so in C, it doesn't give you a certain value. So maybe that's actually not what we want, and we might say, oh, that's a bug right away. So what we can do is go float y equals 0, and then we're going to do y equals linear equation, because maybe we want to have an initialized value. So so let's actually start right there, and we'll run this again. Okay, so y equals some random value, x is negative 1. Okay, we're fine with that. Now y is equal to 0 because we've set it equal to 0. And linear equation is the next call. And so x is negative 1, y is initialized to 0. Okay, we're all good. Now what it's going to do, you can see here's the variables up in the upper left, and this is what we were talking about in the call stack. So so right now all that's on the stack is main, but we're about to see that we're going to add to the stack a frame for linear equation. That'll be the very next thing that happens, because what's going to happen is we're going to come up here, and this is our next breakpoint for linear equation. So this is how we go to the next step. So we say, okay, go to the next breakpoint. All right, now you can see, now on our stack, we've got main and we've got linear equation, because now we're in the linear equation. And the variables are m equals 0.5, x is negative 1, b is negative 1. Exactly what we want. Okay, cool. So now we go, okay, go to the next thing. And now y is negative 1.5 and x is negative 1. And that's exactly what we expect. And now we're going to print out the value of x and the linear equation, like what we just got. So we go next, and now we see in our terminal, this is what's printed out. X is negative 1, y is negative 1.5. You can also see that the linear equation stack entry is now gone. We're just in main. All right, now we're going to go to the next thing. Now we've called quad. So now we're up here in quad, and it's going to calculate our values. And in this case, I just came up with some random values for A, B, and C. So, and you can see all of those right here. That's good. Whoops. So yeah, we can see, yeah, y is 0, x is negative 1, a is 2, b is 3, c is negative 5. Okay, cool. Now we're going to go to square. So we're going to add yet another frame to the stack. So you can see main, quad, square. And then the only variable is -1, so that's going to take -1 times -1, so that should be a 1. So we'll go here. And so let's see, we calculate all of this, the quadratic equation, and now we've got our quad output from all that stuff. And so if we step through, now you can see, oh, now we've printed quad. And then we restart our loop. Main is the only thing on the stack because we went to quad, that returned, square returned. Everything's behaving exactly as we expect. And so now we can just keep stepping through here and just watch how things change. And you can see, okay, we're adding to the stack, we're adding to the stack. The stack is clear because those two functions are over. Good. And so we just keep going, keep going. So hopefully you can see this is a useful tool for seeing what's going on in your code and also for debugging your code. That's really what this is for, but we can use it right now just to illustrate what was talked about all throughout the talk on functions, the call stack, variables, all of that. So I hope this is helpful, and also I hope this is useful for when you actually start writing code and you need to debug. A lot of times what we will do, if you don't have a tool like this, you just put printfs all over the place or equivalent, whatever language you happen to be using. You're just printing out, this is the variable, this is its value, and you just print it all out. And you know, that's typically, to be honest, the way I normally debug. But this is a very useful way if your editor provides debugging tools like this. So how might we use functions in games? Well, we can say maybe write an action game. We might have take damage, and we pass it, and we pass in the amount of damage, and then we've got some local variable for health, and we do health minus equals damage. So health equals damage health equals health minus damage. So this is a function that's going to be called all the time. And you could call it with a negative damage value if you say pick up a health potion or something. Or you might have a separate function for restore health, and health plus equals restore value. In a platforming game, or in many other games as well, we might have a jump function where we just do velocity.y minus equals the jump value. In a Metroidvania, we might have a bunch of different abilities, like say double jump or dash or whatever, and then when we touch some item that unlocks that ability, we store that in an array, and we say unlocked abilities for this particular ability is now equal to true, and that means that we can now use that ability. And so this is some array that's going to be checked when the user tries to use that ability, and if it's true, they're going to be able to do it, and if it's false, they won't be able to. Okay, so to wrap up, we want to separate related groups of code into functions. And why? Because it's reusable and because it's maintainable. So we should make a function for any time we have some related set of stuff to do. So for example, our linear equation or our quadratic equation, those should be separate functions. We wouldn't want to do all that code every single time in just our main. Functions can take 0 or more arguments. Functions may, but don't necessarily have to, return a value. And when a function is invoked, a new stack entry is created, and when that function ends, that new stack entry is deleted. So that's just kind of a brief introduction to functions. The next time we're going to actually run through and use all of the stuff that we've talked about so far to make something interesting. So I hope this is helpful. Thanks, and I'll see you in the next one.